So yes, we stopped at this point in the last lecture. So we'll be doing this power spectra of BPSK, QPSK and MPSK constellation schemes or digital modulation schemes, or you can say BPSK constellation. And this would be our final topic for the course. So we'll start with BPSK first. Okay. So in BPSK, the symbol shaping function is defined by g of t is equal to TB, because now for the BPSK, T and TB are same. The symbol interval is same as the bit interval, and hence this is defined for TB, and this is otherwise. So this is like a rect pulse, a rectangular function with TB duration, and this point is root of twice of E by TB. Now, what is the energy of this? Energy of pulse twice of E upon TB into TB. Okay, and that is nothing but twice of E. Okay. Yes, so this is the energy in the pulse. Now, when this gets multiplied with the cosine terms, so 1 by 2 will come from there. So, if 1 by 2 comes from there, so this 2 and 2 gets cancelled, and this E is the total energy, that is the bit energy which you transmit. Okay. In the signaling interval, zero dB, we have in phase component equal to plus minus g of t. Okay, because we have only one component for BPSK, that is in phase, or you can say if you refer cos as in phase, then it is in phase. Okay. Now we will use a formula, set formula. We have used this formula while studying the spectra of the various NRZ, polar NRZ, RZ waveforms. That time I told you that you will do this derivation once you will do the random process thing. Now, after doing all the things, it is a random process and everything, we couldn't find a slot to do this derivation. But anyways, even if we cannot do it, let us know it that ठीक है ऐसा होता है, आप चाहें तो इसको derive कर सकते हैं. So PST and derivation is given in all the textbooks. So PST of a random binary wave, this is important to know, a random binary wave is equal to energy spectral density of the symbol shaping function divided by the symbol duration. Now, what is the EST? This is called the EST. The EST is nothing but mod of, let us say if the pulse is P of t, then it is P of omega square. Okay, this is the energy spectral density. Okay, so considering this, let us see if this is the pulse, if this is G of t, so PSD of BPSK is equal to ESD of G of t divided by T of P. It is nothing but, so this is, let us say, the function of omega, I should write as a function of. With this as the case, if we define this as B of f or omega, whatever, or let me write Or let me do one thing, let me use only F, because then it will lead to confusion. This is equal to twice of EB sinc square sine square pi of TBF divided by pi TBF whole square. Okay, and this is nothing but this is equal to twice of EB sinc square TBF. Okay, let me not write down one thing. Derivation is given in all standard books. Okay, so this is important to remember, this derivation of this formula. Although it would have been interesting to do it, but we didn't do it. So let me just show you that where the EST for such rectangular pulse is derived in, you can say, the Haken's book. Let me give you that reference as well. 1.6 is the example, chapter 1. Okay. Yes. So you can see, so yes, you can see, sorry for the short break. So see 1.51 comma 1.52 equation numbers in Haken's book. Okay. Okay. So you can see those two equations and you will get this thing very easily. So this is basically the PST of the BPSK signal. Okay. So what we can see is that the power spectrum falls off as the inverse square of frequency. Okay. So let us see this. This is given on page number 353. Let us see. So this is your, I think, let me check if this is, okay, 353. This is not working. Yes, so it is here. Yes, so this is, you can see. So what is the plot? The way plot moves is, so this is a normalized frequency. Now why normalized? So that for a fixed frequency, if you change TB, things would change. For a fixed TB, if you change F, then it will change. So we say that let us plot this as a function of FTB, because FTB is like a joint parameter. So FTB, that's why it is called as a normalized frequency. Okay, so normalized by TB. So normalized frequency versus you just divide it by the bit energy, okay? Because if you change the bit energy, it will have a direct impact on it. So let us see what is the impact of this ultimate, what is the shape. So we want to see the shape. So in order to see the shape, we divide it by the standard amplitude. So we plot SBF by twice of EB versus TB into F, okay? So we will get the standard sinc square function. So that is what we are getting. So this has a first null bandwidth of when f of TB is equal to 1. So it means that f is equal to 1 upon TB is the first null bandwidth. So this much is the bandwidth consumption you will assume it will minimum have. And then it just falls down, and this is the square function, and hence this doesn't go in the negative. Okay. So this is this. Now let us come back to the power spectra of QPSK. what happens for QPSK. Okay. So over the, now the symbol interval is T2 of TB, twice TB. So over the symbol interval, minus of TB less than equal to T less than equal to TB, because the width is of twice of TB, it has to be, because we are taking two bits together to form one symbol, both in phase and quadrature phase, and take plus GT or minus GT. Okay, where GT is otherwise. Okay, this we have seen. Let me just show it to you that how do you get this. Let us go back or go up in our notes. Yeah, here I think I did. Yes, this is. So you can say that this cosine carrier and this sine carrier gets modulated by or amplitude modulated by plus minus root of e by t. So I can represent my g of t as root of e by t over the symbol interval 0 to capital T, or minus t by 2 to t by 2, whatever the t by 2 you want to define it. Okay, if I think that will be good if you do from 0 to t, because a lot of derivations then in the book will match to it. Okay, so this is, you can say, is the pulse. Now, important fact about this QPSK is that the two channels are statistically independent. So the PSTs on each of the channels would add. Okay. Now, both the in phase and quadrature components have a common PST, namely E times sinc square T into F. Let us see how do you get it. So what is it? This is this. So twice of EB sinc square TB into F. Okay. So here you get is E times sinc square TB by F. Why? Because this TB gets replaced by T and this twice of EB gets replaced by the energy. Here the energy inside was twice of E. Our energy is this E. So that is what. So एक एक component यानी cosine component की भी PST होगी, sine component की भी frequency PST होगी. अब क्योंकि दोनों statistically independent हैं, तो both of them would add up. Okay. This I am not showing, basically I am not proving. This is left as a homework / self-study. This is important. This means if you want to do, you should do it. Because we couldn't discuss PST in that much detail, otherwise we would have done it. So the in phase and quadrature components are statistically independent. So PST is equal to sum of PSTs on each of it. So this gets twice of E sinc square T into F. Okay. Which is equal to 4 times E of P sinc square 2 TB into F. Why? Because we know that E is nothing but twice of EB and T is nothing but twice of TB. Okay. So let us see if we try now plotting. So now you plot. So this is your S and Q of F, you can see. Okay. So plot the normalized thing, which means we don't want to, we want to see the shape versus you can say twice of TB into F, or you can say TB into F. Okay, it's better to have TB into F. Sorry. So let us see that what is the plot. It is on page number 360. This is okay. So this is your plot. So SB by 4EB. Now to see the shape. Okay. So now you observe that on this f of TB axis, the first null bandwidth is 0.5 now, and for BPSK it was 1. Okay, 1 by TB. So this has decreased now. So the bandwidth consumption has decreased. It is because your symbol interval is now increased. Earlier the symbol interval was equal to TB. Now the symbol interval is twice of TB. So when you increase the width of the pulse in the time domain, in the frequency domain, the sink will have a, you can say, a lobe which is small. Okay, the width of the lobe will reduce. Okay. That is quite obvious because now the change in the signal is happening over an extended time. Okay. So this is the impact it has. Okay. And finally, let us now study the PSD of MLE. PSD. Okay. So this is the last topic for the day or for the course MPSK. Quite simple to derive. So symbol duration is equal to, you can say, TB into log of 2 to the base, sorry, m to the base 2 okay. This I think I have written when we were discussing. So this MLPSK or MPSK, we know that it also is, it is a two-dimensional constellation. It is a two-dimensional constellation. Hence addition का logic आएगा. So we will get that this same twice of E sin square T into F, but things will change. So PST is equal to twice of E sin square T into F, where this is what? T is nothing but TB log 2M, and E is what? This you must know, it is EB into log 2M, because each bit is of energy EB. So you are basically collecting log 2M bits together to create one symbol. So this is your PSD. Okay. So again, what we will do is we will plot the normalized PSD, that is SB, we can call it as SM. Let me use SM as the term. So this is your okay. So this is your PSD, which is equal to SM of F. Okay. So we can plot SM of F versus twice of EB, or sorry, let us say twice of EB. Okay, versus F of TB. Anyways, we want to see the shape, the way it falls. Okay, this is more or less dictated by the sinc function. This has nothing to do with this amplitude. Okay, so let us see the figure. It is page 367. So you can check for different m's. It is now plotted here. Okay, so you check for m equal to 2, that is BPSK. You find that the first null bandwidth is at 1 by TB. Then you check for QPSK, m equal to 4. So first null bandwidth is at 0.5. Then you check for m equal to 8. So the first null bandwidth is even before 0.5. It means the bandwidth now is getting reduced. Okay, so you can say what you can say about the bandwidth efficiency. Okay, see the bandwidth efficiency. Let us see. Okay, let me write down the important term, bandwidth efficiency. What can we say about it? So we know bandwidth efficiency is bit rate divided by bandwidth consumption. Then the units were bits per second per hertz. So this is what we have defined. This we talked about earlier. I think when we were starting this passband communication, so I gave an introduction to this. So I am directly starting this. Okay. Okay. So with this as the case, let me just allow me 2-3 minutes to confirm one thing before we move ahead. Okay. So you realize, let us say what are the two basis functions for passband communication system are phi 1t twice of t cos of okay. Now realize that now this is like what? This is like a rect function, okay? So rect function get multiplied with a cosine term, okay? So rect means it lies from 0 to capital T. So the channel bandwidth required to pass Mbps के signals is B is equal to 2 upon T, okay, where T is the symbol interval. How do you get this? See, this is a rect function, okay, and its width is T. So even if I, let us say if I talk about the frequency canal, this is multiplication of a rect with, okay, let me do that, okay. So this is like a rect function. And its width is capital T, and this is root of 2 by T. Okay, so this gets multiplied by a cosine of 2 pi fct. Now, in the frequency, if I talk of the frequency transform, Fourier transform, then this is two delta functions at fc and minus fc. Two delta functions fc and minus fc. On them, two sinc functions. Why? Because the rect function has the for width of t, it will be having a width of chi. This is 1 by t only, but because of this being shifted, let us say, if that is the case, if I talk of the first null case, so this first null appears at 1 by t. This is 0. And now suppose this gets shifted to some fc. This is f of c. So this is 1 by t and this is 1 by t. So the net will be 2 by t. Okay. So that is what we have written. So the bandwidth required to pass this basis function phi 1t is 2 by t, and as well as the same follows for phi 2t. Okay, so it means we are both are orthogonal, but they are consuming the bandwidth of 2 by t only. So let us now relate each of these terms. So now the bandwidth T is symbol time, which is equal to TB into log 2 of m. Okay, and your RB is what? Bit rate, that is 1 upon TB, which is equal to, so RB is 1 upon TB and TB is nothing but 1 upon log T divided by log 2m. This is equal to log 2m divided by T. Okay. So what is your bandwidth efficiency? Rho is RB by B, which is equal to log 2m by T into 2 by T. So this is equal to log 2m by T. So 2. So this is your bandwidth efficiency. Okay. So you can see that so we can see the table, or we can draw the table for you. This is M and this is your rho. So for M as 2, 4, 8, 16, 32, 64. Let us see the bandwidth efficiency. This is 1 by 2, this is 1, this is 1.5, this is 2, 2.5, and then this is 3. But we have not yet told you about the error. See, error will also increase. Okay, ऐसा नहीं है कि आप फिर तो आप कहेंगे कि हम m बढ़ाते जाते हैं, bandwidth efficiency बढ़ती जा रही है, तो let us increase m. But right now we have not yet said anything about the probability of error. That will also keep on increasing because you are stuffing more points in the signal constellation and your decision regions are becoming smaller and smaller. With smaller decision region, the probability of the received point falling outside that region increases. Okay. So as the number of states M is increased, the bandwidth efficiency is improved. This is called as BE. Let me write it down as BE. C is improved at the expense of error performance. Okay. So this is, I am quoting from Haken. This is from Haken, page 368. Okay. So this is important to discuss to ensure that there is no degradation in error performance. We have to increase to compensate for the increase in M. Okay. So this is what we had to say. Now there is one important thing which is missed. We took a different way or route to talk about this bandwidth efficiency. We took a route of the basis functions, but while defining this PSD, okay, we have not basically gone to this approach of passband communication. Now the thing is that here we are more or less studying the two systems, QPSK and BPSK, without the carrier being involved. We are studying it from the perspective of G of T mostly. So I would ask that you should go means that already you are at your home. You should just sit back and think that how to relate both of them. If I talk of this BPSK as a passband system, I am deriving the PSD first, assuming I think like a baseband, and then I have to translate to the cosine functions, or what do we do? So you will get an answer with respect to this derivation in bandwidth efficiency. Okay. So this is what we wanted to do in this course. One last comment. A last comment is, so real baseband signal, to convert it to passband, when can be done by multiplying it with cosine function of a high frequency. Okay, using what is the, I've told that the function is real baseband, so its spectrum would be symmetric about 0. Okay, this is symmetric about 0. Now I shift it to passband, so simply you multiply it with the cosine function of, let us say this is f of b, so you multiply it with the cosine function, so in passband you will get that this is like this. Okay, this is your f of c. Now it will be exactly at this place, this fc plus fb, fc minus fp, and the corresponding ranges you will get here as well. But the question, so this can be easily done by multiplying with the cosine function. But what about if I talk to you about a general passband system? A general passband. See, everything cannot be baseband, no? It means there can be devices, there can be things which emit frequencies only in a band. So a general passband system. So passband system, that too with real output, because that will exist in reality. Okay, there are a lot of things, there are a lot of systems which won't have a zero DC frequency, or will have most of the content in some higher range. Okay, a general passband system, suppose if I talk of, then because it being real, let us say this has a spectrum like this. Okay, with this as the spectrum, what is the, now the question is, what is its complex? Now why I'm saying complex, it would be complex baseband रिप्रेजेंटेशन. क्या कोई ऐसा सिग्नल एग्जिस्ट करता है बेसबैंड में जिसको मैं अगर पासबैंड में लेके जाऊं तो वो ऐसा दिखे? ये क्वेश्चन है. This is very important for the course. Course should have answered it, but we couldn't complete it. But for this derivation, for this important derivation, this is important. This important should come here. For this important derivation, you may refer to appendices in Hacking or other textbooks. Okay. You means the interested reader. Okay. So at this point, we close our course. Okay. So I would wish you all the best for the exams. Try to practice the problems and do well. Thank you all.